And so now we begin the content for test 2. And I want to point out here that test 3 is the hardest test that we will have in Calc 1. But test 3, you won't be able to even attempt if you can't pass test 2. So test 2 here is really a hill that needs to be overcome, an obstacle. If you can't do derivatives, then there's no way you're going to be able to apply derivatives. And applying derivatives is test 3. Test 2 will be all about getting derivatives. So it is extremely important that you can pass test 2. You have to be able to take derivatives. So, with that said, I hope you really make an effort to burn this into your brain. And let's begin with what I'm going to call here as derivative patterns. And I like to call these patterns just so it's some name I can give that you can easily identify what I'm talking about. And let's start with the only simple example that there is for derivative patterns. And that is a horizontal function. Now, to get our derivative patterns, what we're going to do is we're just going to use letters. So this represents every horizontal function. You just put in whatever number you want for C. And this represents then every horizontal function. And what we're going to do then is we're going to stick this into the limit and find out what the derivative is for all horizontal functions. So let me just write out here really quick the derivative definition. And we're going to plug our information into that. So for a constant function, x plus h is still c for a constant function. And so we'll plug all of that into our limit. So our f of x plus h we know is c, whatever number we want that to be for our horizontal function. And we know f of x is also c. And so there we did. We plugged our information in. And then we'll go ahead and do the limit then. So c minus c is 0. And I talked about this in the previous video, this tricky little limit here, that the 0 over h is 0. And the limit of a constant is always that constant. And that's our answer. And this is the first derivative pattern you should burn into your brain for the rest of your life that you're going to be doing calculus. Because this is the derivative for all constant functions. And this is our first derivative pattern. The derivative of a constant is 0. So if I ask you, what is the derivative of the function 10? Its derivative is 0. The derivative of a constant is always 0. What if I ask you, what's the derivative of minus this number? Well, the derivative of a constant is always 0. What if I ask you the derivative of pi? Pi is a number. Pi is a constant. The derivative of a constant is always 0. Another one that messes with people's brains a little bit, the derivative of e, another important constant in mathematics. E is approximately 2.71. It is a number, just like pi is approximately 3.14, and the derivative of a constant is 0. This is the first derivative pattern that you should burn permanently into your brain. These derivative patterns, and I truly mean this, these derivative patterns that we're going to go through, you should burn into your brain like you know 2 plus 2 equals 4. You want it to be that fundamental to you, that when you see a constant, you're just like, bang, I know that derivative is 0. Just like when you see 2 plus 2, you know, bang, right away that's 4. That's how much you want to burn these patterns into your brain. And our first pattern here is the derivative of a constant is 0. Now, unfortunately, this is the only easy pattern to demonstrate. And I don't want to leave you completely hanging here on how we get some of these other patterns. And I do want to go through another more complicated pattern here that will be the next pattern you need to memorize. However, you don't need to know any of this proof. None of this will be on the test. There's no homework about it. But I do want to show you how we go about getting at least one more pattern here. And that's going to be for the function x to the n. Now, what does that mean? Well, that means any function, any x, an x raised to any number. So that could be to the minus 1. This could be maybe 213, when n is 213. So we're looking at functions that are in this form, even like x squared. What is the derivative of a function of x raised to some power? That's what we want to find. And here's our derivative definition. And the first thing we need with the derivative is f of x plus h. And so I'll just put that over here. And this is the hard part for this limit. So here I plugged in the information. Here's our x to the n. Here's our x plus h to the n. Just plugging it into the limit. This x plus h raised to the n is the real challenge here in doing this limit. And let's just take a look at that for a moment, because how we go about dealing with this is actually through Pascal's triangle. So if you've heard about Pascal's triangle at all before, it results from doing 1 plus a variable raised to a power. So all I'm doing here is distributing this. So 1 plus y squared, if you distribute all that, is 1 plus 2y plus y squared. I am writing these ones here. I know it looks a little bit goofy, but that'll make sense in a second. But this is Pascal's triangle. And it has all ones on the outer here. And if you look at a number somewhere, notice the number is always the sum of the two numbers above. So 6 is 3 plus 3. If we look at 10 here, 10 is 6 plus 4. 5 is 4 plus 1. So there's a nice pattern here. And mathematicians have figured out what this pattern is. It looks pretty scary, but there it is. Got some factorials in there. And we don't really care about all this more scarier stuff. So I'm just going to simplify this expression to take this complicated thing. I'm just going to call it A. This complicated mess here, I'm just going to call it B. And this is our expression we have for 1 plus y raised to the n. Comes from Pascal's triangle. And there it is again. And we're going to use this to deal with x plus h to the n. So let's just take off the n for a moment, because x plus h, we can factor an x out. And I think this is something that gets lost sometimes in learning math, that you can factor out anything you want, even if it's not there. So, for instance, let's say I have x plus 1. Well, there's no t there, but that doesn't mean I can't factor out a t. That just means I'd have x divided by t plus 1 divided by t. If we factor the t out, you can factor out anything you want. So in this case over here, we're going to factor out an x, and you can see if you distribute the x again, you get x plus h. And if we raise all this to the n, because that's ultimately what we need, and if you remember properties of exponents, this n can pass along to the factors. So this n can pass along to the parentheses, this n can pass along to the other x. And if we do that, this 1 plus h over x is now in the form of Pascal's triangle, 1 plus y raised to an n, where we recognize then that y is h over x. And with this, we can then insert Pascal's triangle then into 1 plus y to the n. And so that's what I'm doing right here, replacing 1 plus y to the n with our result here. And I'm going to plug h over x back in for y. And so we get this expression here. And again, I am going through this a little bit quick because it's just meant to help you understand that these patterns do come from math. They aren't just made up. So I'm going through a little bit quick because it's not going to be on the homework or anything. But here's our expression where we're at. I'm just going to put it back up here again. And now we're going to take this expression and plug it back into the limit. And so that's what I did right there. I just took our expression, plugged it back into the limit, and just rewriting it up here again. And now we're going to do another maneuver that doesn't, I don't know what the right word here is, that doesn't seem, I guess students feel like this isn't a valid thing to do, maybe is the right way to say it. But if you have a times b plus c plus d is previously in probably all your math classes, you've been told, just distribute all that out. And you can, there's nothing wrong with that. But you don't have to distribute it fully. We could distribute the a just to the b and say a times b, and then we could acknowledge that we're not going to distribute it to the c and the d. And we can do that. So something I think that is, some people I think maybe feel is wrong or something, but you don't have to distribute the a to everything. Nothing says you have to do that. We can distribute the a to just the b and then keep the parentheses around the c and the d. And that's what we're going to do over here. This x to the n, we're only going to distribute it to this 1. And why would we do that? Because then we would have x to the n minus x to the n, and those will subtract out. And so that's what I'm doing here, is the x to the n I'm only distributing to the 1, so there it is. And then the x to the n I'm not going to distribute to everything else, and so now I put the parentheses around that. And now these x to the n's subtract out, and they're gone. And so here's our limit expression. I'm just going to rewrite it again up here. And division by h we can write as multiplication by the reciprocal. And now what I'm going to do is this 1 over h, I'm going to distribute now into every term here. So every term in the parentheses will be divided by h. So this h will go away. This h squared will become just h. This h cubed will become h squared. And so that's what I did in this next step. I distributed 1 over h into the parentheses, so that h is gone. This h squared is now h. This h cubed is now h squared. And I'm going to use a property from the limit. Remember, the limit can pass along to factors. So I can take the limit and pass it to the xn, and I can take the limit and pass it along to this entire parentheses here, because it is a factor. And x to the n, there's no h here in x to the n. So as h goes to the 0, x to the n remains unchanged. And so this first limit here is just x to the n. And now we have the limit of everything else. And this may all seem maybe complicated, but this is actually a pretty neat little thing that happens here. Because you remember, the simple thing to do is if you plug in 0 and it works, then it works. So what happens if we take the limit of all of these terms? So I distributed the limit into the parentheses. Well, n times 1 over x. There's no h there. So as h goes to the 0, this remains unchanged. Now what about this next term? Well, here's an h. So as this goes to 0, that whole thing goes to 0. And there's also an h over here. So as this h goes to 0, this whole term goes to 0, and so forth. In other words, every term in the parentheses has an h except the first one. So as the limit goes to 0, all the terms disappear except the first one. And that's our answer. We just figured out the derivative for all functions that are x raised to the n. And ultimately, this pattern then is written as n times x raised to the n minus 1. Now, you don't need to know this proof in any way. I just wanted to show you that these things are all derived from math. But what you do need to burn into your brain is this pattern. This is called the power series derivative because it's a power function. And what I just showed here on the right is the derivative of a power function is always n times x to the n minus 1. That's what on the right here we just figured out. And this is the second derivative pattern you need to permanently burn into your brain. So we have 2 derivative patterns. Permanently burn them into your brain. Let's check out some examples of this new pattern here. So let's say we have x squared. What is the pattern telling us? The pattern is saying, well, identify what n is. N is 2. And so the derivative is saying, okay, put an n here, and then put an n here. And then 2 minus 1 is 1. And that's the derivative. And this is a derivative we already did by hand with the limit. And now we're going to use these patterns. We're going to exploit that these functions always have the same derivative form. Why keep doing the limit when we know the answer will always be in this form? And so now we're going to remember these forms instead of going through this limit all the time. So how about x to the 5th? What is that derivative? Well, the derivative pattern says identify n. N is 5, and so we'll put in a 5 everywhere there's an n. 5 minus 1 is 4, and that's our derivative. The derivative of x to the 5th is 5x to the 4th. That is the derivative. So your ability to deal with exponents is going to be very important algebra knowledge for you here because of a problem like this. What is the derivative of 1 over x? Well, remember, 1 over x we can write as x to the minus 1, which means this is a power function. It is x raised to a power, and that's our pattern. So if we look at this, we identify n as minus 1. So we're identifying n as minus 1. So we'll plug in minus 1 all over there. And minus 1 and minus 1 is minus 2. And that is the derivative. And if you wanted, you could rewrite this back into a ratio. And MyMathLab does state a lot to write your answer with positive exponents, which means MyMathLab will want this answer. Now, in the real world, there's normally nothing wrong with this answer, but MyMathLab will state many times, write your answer with positive exponents, and this is what they mean. They want this answer here. Let's try something that combines the two patterns together. So let's say we had 2 plus x cubed. Or I typed a 4 in there, but my brain said 3. So 2 plus x cubed, and let's figure out this derivative. And I want to be a little bit technical here to stress what's happening, but taking the derivative is just like taking the square root of both sides, or adding 2 to both sides, or dividing both sides by 10. What we're technically doing here is we're taking the derivative of both sides. And this notation here that you will see going forward, this d over dx, this is called an operator, and operator has to deal with some more advanced math stuff you'll see in the future. But for now, d over dx is simply an instruction telling you to take the derivative. And so this is what I will stick on both sides. D over dx is an instruction saying we're going to take the derivative with respect to this x. And so this is the notation of taking the derivative of both sides. And on the left, here's where we would just write then this f, this function, this function here is just going to slide up right next to the d. And so this is our df over dx. Remember, that's our notation that means this is the derivative. And on the right side here, the derivative distributes. So again, d over dx think of it as a command. It's saying take the derivative of this thing that's next. So, what is the derivative of a constant? Well, that's our first pattern. The derivative of a constant is always 0. And what's the derivative of x cubed? Well, x cubed is our power function. And the derivative of x cubed will be 3x squared. And that's our answer. Here is our function. And here is our derivative. So remember, the derivative distributes. that comes from the limit. Remember, the limit distributes. The derivative is a limit, and the derivative also distributes. And that means we can take the derivative of terms individually then. Let's check that out again. Let's say we have instead, let's say we have x to the 10th minus 5x plus 4. So we're going to take the derivative. And we can take the derivative term by term because the derivative distributes. So I'm just going to write that out. Because the derivative distributes, we can take the derivative term by term. So I'm just going to write that all out. Normally, people don't write all this out, and they just do the derivative of each term. But that's what it would look like if we wrote it out. So let's do this first command. It's commanding us. Do the derivative of x to the 10th. Well, we identify x to the 10 as a power function. And then we identify n here as 10, which means its derivative then will be 10x to the 9. Now this next one, and actually let me put over here on the right these patterns that or these properties that we have. So what I'm saying here is a property of the derivative, and this comes from the limit. We already have shown this with the limit, but let me write this again with the derivative. That an enormously useful property is the derivative distributes. So we can take the derivative of f and then just add that to whatever the derivative of g is. And so we can write this then like so. And so here is our derivative properties. Is the derivative distributes. And another very useful property that comes from the limit is, let's say we have some constant times the function. If you recall from the limit, a constant we can pull out of the limit. And the same is true with the derivative. If we have a constant times our function, we can pull that constant out of the derivative. And these are our two properties we have so far. Talk about more in next videos. The derivative distributes, and any constants that are factors we can pull out of the derivative. And these both come from the limit. These are also properties of the limit. So what does that mean for the problem we're working here? Well, we're taking the derivative of 5 times x. 5 is a constant factor, and we can pull it out of the derivative. And what is the derivative of x? Well, the exponent here is 1. So if we go to our derivative pattern, we would have n is 1, so we would have 1 times x raised to the 0. and x to the 0 is 1. And the derivative of x is 1. And something else I want to point out here is that with this notation here, that this whatever is sitting in front of the derivative here, so here is the derivative command. This is what's telling you to do the derivative. What's ever next to it here, we can actually slot right into that numerator there. That's always something we can do with this notation. And you can see dx divided by dx is 1. So there's all a nice consistency here. The derivative of x is 1. And the derivative of a constant is always 0. And that's our answer. So here is our function, x to the 10th minus 5x plus 4, and its derivative, 10x to the 9th minus 5. And again, notice we did the derivative of each term. We did the derivative of x to the 10th, which is 10x to the 9th. We did the derivative of minus 5x, which is minus 5, and the derivative of 4, which is 0. The derivative distributes, and we can do terms then individually. So let me do one that I'm hoping will look kind of messed up. So why don't we try this? How about 7, 8, and let's go for maybe a 6 there. Maybe a 2. So that looks like a mess. Here is our function. Now, if I asked you to get this derivative with the limit, that would be a serious pain. But we have our patterns now. And all of these functions, there are 1, 2, 3, 4, 5 individual functions here, and they are all power functions. So a good first step here is to write everything as a power function, which means using properties of exponents right here, because 1 over x to the 2 is the same as x to the minus 2. And 5 divided by x to the 4th is the same as 5x to the minus 4. And that's a good first step, to write everything clearly as power functions. And now we're going to take the derivative. And because the derivative distributes, means we can do each of these functions individually. So for instance, 7x to the 8th. Well, let me just write this out here. We're going to do this first derivative here. Well, actually, let me just paste this everywhere here. So the derivative distributes, so we can do the derivative of all of these terms individually. So this first derivative here, let's go back to this first one. 7 is a constant factor, so we can pull that outside the derivative. And then x to the 8 is our power function. And then we identify n as 8. And so we'll just plug that into the pattern. So x to the 8, that derivative is 8x to the 7th. And that's our derivative right there. 8x to the 7th. So what about this next one? Well, the 5 is a constant factor, so we can pull that outside the derivative. And then what's the derivative of x to the 6? Well, this 6, I like to say, drops down right here, and then you subtract 1. So 6 minus 1 is 5. And that's that derivative. What about this next one? Well, 4 is a constant factor. Let's pull it out of the derivative. And then the derivative of x squared is 2x. The 2 drops down, and then you subtract 1 from the exponent. So 2 minus 1 is 1. And that's that derivative. So we'll go on to this next one. So the exponent drops down, and you subtract 1 from the exponent. So minus 2 minus 1 is minus 3. And then on the last one, we have another constant factor, 5. So we can pull that outside the derivative. And then we need to do the derivative then of x to the minus 4. So the minus 4 drops down, and we subtract 1 from the exponent. So minus 4 minus 1 is minus 5. I'm just going to put that one in parentheses there because it is going to be hitting this other minus sign there. And so we'll have minus times a minus is positive. And 5 times 4 is 20. And then as our final cleanup step here, 7 times 8, 56. 5 times 6, 30. 4 times 2, 8. And that's our answer. Here is the function, and here is the derivative. So let's check out another one. And I am purposely picking ones here that I know students tend to have trouble with when they first learn derivatives. And another one that tends to mess with people's brains a little bit is dealing with the square root. And actually, before we do this one, let me say quickly, about what this, oops, that's not what I wanted to do. What it means to have a fraction in an exponent. Let me just talk about that really quick. The 2 in the numerator, the 2 is the power. So the 2 means x squared. That's what the 2 means. The 2 is the regular power you're used to, like x squared, or if that was a 4 there, it'd be x to the 4th. The 3 is the root. So we're going to do x squared, and then we're going to take the third root. Or we could do the third root and do x squared. Either way, doesn't matter the order here. But the point I want to make here is that we can write this as x squared, because that's what the 2 means. It's the power. And then we would say that this is then taking the third root of that. Now, another way to write this, the more clunkier way that's not calculus friendly, would be to use the square root symbol. The square root symbol is not calculus friendly because it's not a number. So another way you could write it is that. Different ways to write the same thing. But the point here is the numerator is the power and the denominator is the root. So if we have the square root of x, the first thing we're going to do is get rid of the square root. And because it's not a number, we can't manipulate the symbol, but we can manipulate a number. And a square root does mean power of a half. The square root is a power function, and so its derivative is just following the power pattern. The 1/2 will drop down and then we subtract 1 from the exponent. So a half minus 1 is minus a half. And that's our derivative. Now, most likely, MyMathLab will want this written as positive exponents. And so to write this as a positive exponent, we'd have to move the x into the denominator. Which we could also write again then as 1/2 square root of x. Now, MyMathLab's not picky between these two. It is picky on this one, though. So to try to get answers the computer can grade, it always wants you to write positive exponents. And that's our answer. That is our derivative. And this derivative you actually have already done with the limit. But now we're doing it with the patterns. We try another one with fractional exponents. How about, let's add a constant in there. Say 5x to the, we'll say 3/4. So this means x cubed, then the 4th root. And what is the derivative? Well, let me write this all out. So put the derivative instruction there. We're going to take the derivative of this. 5 is a constant factor, so we can pull it out of the derivative. And here's our power function. When we take the derivative, the 3/4 will drop down. And then we subtract 1 from the exponent. And 3/4 minus 4/4 is minus 1/4. And that's our derivative. We'll clean it up a little bit because 5 times 3 is 15. And while this is a perfectly acceptable answer, MyMathLab wants positive exponents. So let's do that, which means x to the 1/4 will drop into the denominator then to make that a positive exponent. And if for some reason you find attachment to the radical symbol, you can always use that as well. And I actually chose the wrong symbol there. I need to choose the one that's got the input there. And there's our answer. And again, these two, MyMathLab should accept both these equally because they both have positive exponents. But I do want to make clear, because you are all learning this, and I know you want to get the right answers, so you listen to MyMathLab, but there's nothing wrong with this answer. There's nothing wrong with it. MyMathLab just wants you to write it as positive exponents. So for this first homework, I'm going to be jumping around a little bit in the book. The book has all good information. It's all good information. I just don't like the order that they're presenting it. So I don't want to give any misleading ideas here. The book has all good information. I just don't like the order of presentation. I want to talk about these derivative patterns first. And I'm going to show you a screen here. It may be scary at first. And I will also have this file available for download so you can print it out. And here it comes. Here is basically all of test 2. And again, I will make this available for download so you can print it out. These are all the derivative patterns that will be expected of you this semester, and derivative properties, including 3 we have not talked about yet. But this sheet is an excellent guide for derivatives. So right off the bat, if you notice, here's our constant functions derivative. Here's our power function. Another pattern, the exponential, the derivative of log, the derivative of these 6 trig functions. Here's our derivative patterns, the derivative distributes. We can pull a constant out of the derivative. And the rest of the week, we're going to talk about these other 3, the product, quotient, and chain. These patterns, all this information on this page will be ingrained knowledge in your brain as you go through calculus. This information on this page will become like 2 + 2 = 4. That's how burned into your brain this will become if you have calculus going into the future. So I want to show some of these other derivative patterns here in practice. So let me make a new function here. And let's incorporate some of the new patterns we haven't talked about yet. So how about an exponential function plus a log function? Let's check that out. So the constant function we proved, the power function, I went through that proof kind of quickly. All these other patterns I'm not going to prove. You're going to have to seek that out on your own if you're interested in. And you're just going to have to accept these as fact. I promise you they're facts. So let's check this out. We want to do this derivative. And let's look at what it says for exponential functions. It says if you have a number raised to x, which is what we have right here, a number raised to x, exponential function. The derivative is always natural log of that number. So our derivative will be the natural log of this number, the base, times that exponential. And that is the derivative. And I want to stress, because it's something easy to remember, so I'm looking at exponential functions here. The derivative of an exponential, b to the x, notice its derivative always contains b to the x. So a thing I like to say is the derivative of an exponential always contains itself. So here's b to the x, and the derivative also has b to the x in it. It's just multiplied by this number, log b. The derivative of an exponential always contains itself. And if we look at the logarithm pattern, so here's the log pattern, log base b of x, this derivative will always equal 1 over the natural log of b to the x. So this derivative here is going to be, looking at the pattern, 1 over the natural log of the base. The base in this case is 5 times x. And that's the derivative. Now, something I like to say with log functions is, this is always true for the log, the derivative of log is always 1 over x. So an exponential, the derivative always contains itself, and the derivative of log is always 1 over x. And on the left, that's our answer. What about some of these trig functions? So let's say we have this trig function here. Well, how are you going to know how to do this? Because you're going to burn these patterns into your brain for as long as you're going to be doing calculus. Personally, I will probably be on my deathbed and still remember these patterns. So, let's check this out. And let me just write this all out with the derivative. It's called an operator technically, but I like to call it a command just to imprint upon you that it is an instruction telling you to do something. So we're going to take the derivative of 3 sine x. 3 is a constant factor, so we can pull that outside the derivative. And then now because you haven't burned these into your brain yet, we will look to our patterns over here. And here is the derivative of sine. The derivative of sine is cosine. So the derivative right here of sine, the derivative of sine is cosine. And that's that derivative. So if we look at the next one, 5 is a constant factor. So we'll pull that outside the derivative. And now you haven't memorized what the derivative of cotangent is yet, so you'll go over here and look at the derivative patterns. And right here is the derivative of cotangent equals minus cosecant squared. And because there's a minus in there, let me throw a parentheses up. So the derivative of cotangent is minus cosecant squared. And then minus times a minus will be positive. And there's our final answer. The derivative of 3 sine x minus 5 cotangent x, that derivative is 3 cosine x plus 5 cosecant squared of x. So there's something else I want to, there's so many things to say about the derivative here, but just for this first section here, something else I want to say about these patterns is why, one reason why the number e is interesting is because of its derivative. So let's look at the derivative of e to the x. And let's look at what our pattern says. So exponential functions, the derivative of a number raised to the x is log of that number, natural log of that number, times the exponent. Again, the derivative of an exponent will always contain itself. And what is the natural log of e? It's 1. The derivative of e to the x is itself. And the only other function that has that property actually is 0, because the derivative of 0 is 0. Remember, the derivative of a constant is always a constant, including 0. The derivative of 0 is 0. And the only other function whose derivative is itself is e to the x. Another reason why e is a special number, its derivative is itself. And another interesting thing that falls from base e is the log. And now this is something that you have seen in algebra, hopefully. I want to make sure, though, that you remember this. Log base e is natural log. So let's do this derivative. What is the derivative of log base e, which is the natural log? Let's take a look at what the pattern says about that. So if you look at log functions, the derivative of log base b to the x equals 1 over the natural log of the base, in this case it's e, times x. And what is natural log of e? It's 1. And so this is another special case. The derivative of the natural log function is 1 over x. And now, does this mean something else you have to remember? Not necessarily. Remember, both of these patterns come from the derivative pattern. The reason that these simplify is because log e is 1. So these are special cases of the exponential and logarithm patterns when you have base e. Because log e will be 1 and you lose that log thing. So the derivative of e is itself. The derivative of natural log is just 1 over x. And I just want to state again, these patterns come directly from the patterns on the right. So these aren't 2 new patterns you have to memorize. That's not true. They come from these patterns over here. But it is good to know that base e is special. And that's because the log e here is 1 then. It makes these patterns a little simpler. There is also another maneuver in some of the homework problems that I want to talk about. And this maneuver is actually very helpful for very many things in math. Let's say we have this function and we want to figure out the derivative. Well, we don't have anything in our patterns that looks like this. There's nothing over here that has division in our patterns. So how are we going to deal with that? Well, there is a way to deal with division, and it's called the quotient rule, which we will talk about in a couple more days. But you do have homework that's like this, even though we don't have quotient rule yet. But what I want to show here is this very useful maneuver that's used in more places than just derivatives. And that's decomposing this back into fractions. And this is something that I've just found through experience a lot of students seem to forget that we can do. Because, you know, if you think about most of your life, you've been adding fractions together. And so that's what you're used to. And now all of a sudden coming into calculus, you're going to find that actually breaking things back into fractions can make things easier. And so I just want to point this maneuver out. Try not to forget this. But we can divide every term in the numerator by the denominator. We're going to decompose this back into the fractions that it could have come from. And that's all I did. I just decomposed this back into fractions. And I know that may seem unusual, again, because you've added fractions for so many years of your life, that it may seem unusual to go backwards now. But this is a very useful maneuver for making things simpler. Because x divided by x is 1, and 1 divided by x is x to the minus 1. And these are both derivative patterns that we know. And so what is the derivative of this function then? Well, the derivative distributes, so we can do each term individually. The derivative of a constant is 0. And the derivative of x minus 1. The minus 1 will drop down. And then we subtract 1 from the exponent. And that's our derivative. So the derivative of x plus 1 divided by x, that derivative is a minus x to the minus 2. But the main purpose of this was to show you this step of decomposing into fractions. Very useful step that you will see throughout our semester, also going into Calculus 2, Calculus 3, a very useful step. There's also another idea I want to get across that I think is extremely helpful for putting this all together. And what I like to do in class is I like to use circles and squares. I'm going to do my best here to find some circles and squares. Looks like I got a triangle. We'll call that a circle. And let's see if I have any type of square. I don't think I have a square anywhere. Oh, here's one. Perfect. Now, if I wrote this out, all of our brains can easily identify a triangle, a circle, a square. What I think is going to be incredibly valuable to you going forward is if you can do the exact same pattern recognition with functions. What I'm hoping you'll consider is when you look at a function that you can identify what you're dealing with. Now, let me say that again. If you look at this, you immediately understand you're dealing with a triangle, a circle, and a square. It's just pattern recognition. You know what these things are. When you look at this and see a triangle, I want your brain to think the same way when you see this x squared. When you see this x squared, you want to name that. That's a power function. Just like when you look at this strange object here, You recognize this is called a triangle. You want to do the same thing with functions. You want to look at this x squared and identify it as a power function, because then you know what its derivative is. Then you want to look here. You want to name this. You want to identify this as a constant function, so you know the derivative pattern to use. And then you want to look over here, and you want to recognize this is the trigonometric function of sine, so that you can go to the sine pattern and get its derivative. And this is going to be very important going forward as things get more complicated, that you can look at a function and identify, is there a power function here? Is there an exponential function? Is there a trig function? You want to be able to identify these things so you know what derivative pattern to use. And this identification I consider to be just like this triangle, circle, square. You see this object, you know it's called a triangle. When you see this object, you want to know this is called a power function, so that you know what derivative pattern to use. And I'm going to make this shape analogy more as things get more complicated, to try to help you see more of the simplicity. I don't want to pretend like this is simple, but I do want to try to show you the simplicity of things where I can. And being able to identify the components you're dealing with is very valuable going forward. So as one last example, I want to show you what is probably a good way to begin these problems, and where I hope you will eventually end up going with this. So let me just write out something here. And we've done enough of constants. The derivative of a constant is a constant. The derivative of a constant is 0. Let's do some of the more challenging looking ones. And maybe we'll throw a log in there. And how about another trig function? Let's go with one that you don't see too much. How about secant? So let's say this is your homework problem. Now what I think, of course, whatever works for you should do. I'm just giving you some guidelines in case you don't know, you don't have an idea of how to start all this. But I think a good way to begin learning this is to be thorough in what you're writing down. So what we're going to do, what do we technically do first? What we technically do first is take the derivative of both sides. This is technically what we are doing first. And so if I was going to write this out thoroughly, this would be my first step I write out. And now on the left side, this f, remember whatever's in front of the operator, we can always slide into the numerator position there. And normally when you do this, you just kind of drop this off. That's just all personal preference. You can keep it there if you want. That would not be wrong. But that just slots into the notation there. And then on the right side, the first thing we would do is distribute the derivative. That'd be the first thing we do here. And we don't need the parentheses anymore because we've distributed the derivative. So if I was writing this out thoroughly, this would be my next step. And now the next step, if I was doing this thoroughly, is I'd pull out all these constants. So this 4 is a constant. We can pull it outside the derivative. This 6 is a constant. We can pull it outside the derivative. This 8 is a constant. We can pull it outside the derivative. So again, this line here distributed the derivative. So use this distribution property. And the next step, I use the constant property, that the constants we can pull outside of the derivative. And now the next step in being thorough here would be then to do the derivatives. So first off, we have the derivative of cosine. Since you probably haven't memorized that yet, we'll look at the patterns over here. The derivative of cosine is minus sine. So right here, the derivative of cosine is minus sine. What about this next derivative? 1 over x cubed. Remember, 1 over x cubed we can write as x to the minus 3. And then what is the derivative of x to the minus 3? Again, you identify this as a square. Going back to pattern recognition, identify this as a power function. And so the minus 3, I'm just going to use the parentheses here because we'll have some minuses here. So the minus 3 drops down, and we subtract 1 from the exponent. So minus 3 minus 1 is minus 4. And that's that derivative. Now if we go to the next one, log base 2, so we'll go to our log pattern here. And the derivative of log base 2 is 1 over natural log of 2. 1 over natural log of 2 times x. So that's right from the derivative pattern there for log. And then finally secant. So if we look at secant right here, the derivative of secant is secant tangent. So the derivative of secant is secant tangent. And that's our answer. And we could clean it up a little bit, not really too much though. So 4 times minus sine x would be minus 4 sine x. Minus and minus here is a positive. And 6 times 3 is 18. Over here, not much we can do, except maybe slot the 8 up here into the numerator. And that's all the cleanup we can do. Here is our best simplified final answer. And I'm going to take this and use it again. So this was going through it thoroughly, step by step. And I encourage you to do this for now. And the reason I encourage you to do this is so you can understand the logic of how things are happening. Once you're confident with your understanding of how things are happening, then what happens with most students is they tend to stop writing all those steps. So let's just pretend this is a new function that we're going to take the derivative of. But instead of writing all the steps out, I'm just going to do it right off the bat. Now, can you do this yet? No, probably not. the point of this here is to try to show you where I'm hoping you will end up. With enough practice, and if you burn this into your brain, then you'll find that you're not going to want to write out a lot of those steps. So for instance, if we want to take this derivative, well, what's the derivative of sine x? It's cosine x. So the derivative right here, the derivative of sine is cosine. What about the rest of this here? Well, remember, we can do derivatives term by term. So if we take the derivative of this next term, we know the minus 4 drops down, and we'll multiply that 18. And 72, and that drops down. And we subtract 1 from the exponent. So minus 4 goes to minus 5. What about this next one? What should we do with this? Well, if x is in the denominator, we should write that again as a power function so that we know we're using the power pattern for the derivative. And what is the derivative of x to the minus 1? Well, the minus 1 will drop down, so we'll multiply all that by a minus, and we subtract 1 from the exponent. So minus 1 is minus 2. And then finally, what's the derivative of tangent? We'll go to our patterns over here. The derivative of tangent is secant squared. And we're done. Here's the function. Here is the derivative. Now I want to stress again that this is where I'm hoping you will get to. Can you do this yet? Probably not, because you're just learning it. I'm hoping you will get to this point, though. Because if you do, if you can see a function and go right to writing its derivative down, then that means you're burning this stuff into your brain. And I promise you, if you can burn all this stuff into your brain, your life in calculus will be much easier. You will see these, you will see everything on this page. You will see for the rest of your life if you have a career in calculus. So this first homework assignment for our test 2 material is going to be simply, can you do these base derivative patterns along with these 2 properties? So the first homework is going to contain all these patterns and these 2 properties. Whoops, not the product there. Well, I can't highlight constant and distributes, but these 2 properties here. And then through the week, so the next lecture, we're actually going to talk about product and quotient. And then after that, we're going to talk about the chain. And the chain rule is where we can deal with very complicated things then. And our functions will be getting a lot uglier than what you're seeing here. So please, please burn this into your brain. So as things get harder, you won't struggle with these patterns. And in the next lecture, we will talk then about how you do derivatives. How do you do derivatives if you have things multiplied by each other? Like that. How would we do multiplication? That's the product rule, which we will talk about in the next video.